And now we're going to pivot. And in fact, that last discussion is a perfect pivot really to this next section. So we're going to move from the clinic back to the medical device industry and hear from some researchers who are actually capturing the clinical experience back into the lab so that they can use the real human experience, the clinical experience, to optimize procedures and devices. And so with that, I'd like to invite Kevin Sack up to the stage. Kevin started, I won't embarrass him completely, but he started, he'll correct me, 7, 8 years ago, I believe, as an intern, as an undergraduate intern on the project. And now he's leading, you'll see the work that he's doing, changing the development of heart rhythm management. Kevin?
It's a real privilege to be here, and Steve, thank you for inviting, and thank you to the Living Heart Project for organizing another symposium that's enriching and enjoyable to attend. My talk today focuses on looking at heart rhythm management, which is the major area that I guess our functional group in numerical modeling in Medtronic does. We do a lot of computational modeling at Medtronic. We touch every stage of the device, from research all the way through development to regulatory submissions, even post-market monitoring. The focus of my talk today is really quite a niche research topic using a full heart model, and it looks at, should we extend AV delay for patients that have extended P wave duration? I mean, first of all, what does that mean? Maybe I should give a little background. If the clicker works. Great. So I've got a QRS signal up there, well, an ECG strip. And what the P wave is that's the part of the ECG signal which we can get from electric potentials on the surface of the heart. Even our devices that are connected can look at potentials. And something is happening. That's okay. I'll keep on going. So the P wave essentially gives us, through electrical signals, an idea of how long the atria are contracting. So if we look at the duration of that electrical signal, we have an idea of how long the atria contract for. The QRS complex, which will come up in 1 second, has to do with when the ventricular structure contracts. And essentially what guided this research was we had some experience previously, clinical and preclinical studies looking at human data, and it was really noisy and messy. And we were sure a signal did exist, right? Because that delay, that AV delay, is incredibly important for synchronous behavior. We needed to understand how the heart functions, or we need a fine tune of it to optimize cardiac function. And for patients that are sick, that optimization can be quite critical. Tech at the back, do you need me to come help? No, you're all good. Okay. So for instance, I'm going to go back just 1 second. For instance, we know that if the AV interval is too long, that can be really bad and gives patients an increased risk of heart failure, even atrial fibrillation. And so usually we're a little bit conservative about trying to normalize what that AV delay should be. So specifically what we're looking at is patients that have slower atrial activations. Can modeling create insights to tell us what their specific AV delay should be? Well, it's been really hard to prove clinically, but a model can isolate effects in a wonderful way. So let me show you that model that we're looking at. Right. So this was a patient that needed, that had left bundle branch block, which is a type of electrical dysfunction that requires pacing. This patient had a little bit too normal, if that makes sense, of a geometry structure. So we morphed it a little bit to be representative of dilated cardiomyopathy. So we dilated the atria, we dilated the ventricles, we reduced contractility in our model, we made the chambers stiffer, We increased diastolic pressure and we increased left atrial pressure, really changing structure and hemodynamic function to be representative of a really sick patient that needed pacing. And here is some animations of this heart when it's beating. Here you can see the whole heart on the left-hand side beating together. That's just a cutaway plane, so you get an idea of what's happening inside of the heart. And then we take this model and we couple it to a lumped hemodynamic circuitry model. So we can not only just tell in a single cardiac cycle, but what the consequences are of repeated cycles and the stable limit that it reaches with our intervention. Right, so specifically, atrial delay, right? Atrial contraction, how long it takes. So that P-width duration. What we did is we really changed one major thing from model to model in this case, and that was how quickly conductivity in the atria allowed the electrical wave for excitation to propagate. So you're seeing different cases of different P wave durations, 80 milliseconds on the far left, up to 220 milliseconds on the far right. The ventricular activations are a little distracting, but they're the same throughout all cases. So for our experimental design, we looked at 4 different types of atrial activation speeds that resulted in 4 different P wave durations. And then we looked at left bundle pacing that was delayed from 100 milliseconds all the way to 340 milliseconds. So a snapshot just so you can see the comparison between our slowest model and our fastest model. At 80 milliseconds, the 80 milliseconds duration P wave has completely, right, activated the atria, but only a quarter has been activated by our slowest model, right? So a couple of terms that I've already covered. What's quite nice about a model, I mean, people have touched on it before, is that we get, a clear picture of things, and this is true visually when we slice through, but it's also true for interrogating data. So when we get our P wave duration, we're not estimating something from a line. We're actually looking at histograms of every element in the model, looking at their exact activation times, and deriving our metrics in a really precise way. So our P-width duration come from the histogram duration width, right, for the left and right atrial activation combines to give us that P-wave duration. And PAV is a common pacing term, but essentially it talks about the AV delay. And you'll see it in my slides, but just I want you to think of it as AV delay. Now you can see when we modulate some of these things in the model, we get very different looking histograms. So that top row has the same AV delay or PAV of 180 milliseconds. That bottom row has a larger AV delay. And each column has different combinations of that P width duration. So you can really see, I mean, for this case of a fast AV delay, there's no need, just from looking at the histograms, to extend AV delay too far out. Right? You can see there's clearly no overlap. They're activating altogether. While you start running into problems as that P wave duration gets longer and longer with substantial overlap of activation. So this is the first finding that we had in our model. We look at EA ratios. It's a common echo metric that clinicians pull out to look at flow. And essentially, when the heart fills, first passively, the valve opens and blood goes into the ventricles. And then the atria contract. And those two flow events are labeled E and A. And essentially what you want in a functioning normal heart is 2 really well-defined E and A waves. And what we have, when you take a look at this model, with the black line being the slowest activation curve, is that where PAV of 100 milliseconds AV delay is too short to even develop that A wave. Right? You need to have some time in PAV with P wave duration for a sufficient AV wave to develop. Now, you start to get some issues as well as you get longer atrial activation times. I mean, just take a look simply at that middle case there. I mean, even if everything is well defined and you have a good E and A wave or relatively good E and A wave, that slow atrial activation does diminish function. We're getting diminished A-wave amplitudes purely from the electrical desynchrony or electrical degradation. And lastly, if we take a look at increasing AV delay too much, right, what you start to get is something really interesting because atria contracts, we wait a while, ventricles contract, and it's all happening in a limited time space of a cardiac cycle, you actually cannibalize some of the rest of the time from the cardiac cycle. So you decrease on the following beat the passive filling. So in that last case, you can actually see the E waves are cut short quite substantially. Left atrial pressure. Left atrial pressure is critically important to patients. When you have high left atrial pressure, that can lead to hospitalization, bad morbidity outcomes. You really want to see a normal pressure waveform, which has an M shape, that has an A for when the atria contract and a V for when it's labeled A and V waves for atrial and ventricular contraction. But you want to see it looking like a nice M shape. And what you have here is really some interesting cases. So remember we saw that A wave didn't develop at all in the first case with that really slow purple line of 220 P wave duration. That's because they're contracting essentially at the same time, so you have a merged A and V wave in those atrial pressures with really high peak pressures in the left atrial pressure. That's incredibly bad. You need a substantial amount of AV delay for that to normalize and for you to start seeing some of that M-shaped morphology when the A and the V pressure wave are clearly defined. Now, on the other end of the spectrum, something unusual is happening when AV delay, again, is extended too long. You're starting to see those atrial pressures really rise on the ventricular kick compared to the middle curve, right, or that middle plot over there. So when you have AV delay too extended, your challenge then is that the atria overfull while they're waiting for the ventricles to contract. And then when the ventricles do contract, because they're a connected structure, they're introducing elevated pressures during that contraction phase. So we can also take some hemodynamic metrics, right? LV stroke volume, max left ventricular pressure, and max LV dPdt, which is a proxy looking at the gradients of the pressure trace for contractility. And what we did is we took the peak value or the ideal value that we saw in each of those curves and plotted it as a function of P wave duration. So just for example, if we take a look at that stroke volume, right, I take that peak over there with the yellow curve, the second peak over there for the orange curve, looking at the purple curve, that peak comes there, and I plot those, right, with P wave duration as the function and the optimal AV delay being the y-axis, and we actually get really nice curves. So we can see hemodynamically a clear trend exists for all of these metrics where you get an ideal outcome in stroke volume, max LV pressure, or max LV dPdt that correlates quite strongly with P wave duration. And if we take a look at the atria and the pressures in the atria, the signal couldn't be clearer. So left atrial pressure, looking at the mean left atrial pressure over the cardiac cycle, you get these parabolic curves where it's clear that there is an optima there, right? It's very clear that if you want a reduced left atrial pressure that corresponds with these, improved stroke volumes, right? Again, basically a linear relationship. And the same can be said with the right atrium. So just in summary, we took an electromechanical 4-chamber heart model. We changed P wave duration, just P wave duration, to take a look at how that affected hemodynamic outcomes in the heart. We found that there was a linear relationship, so there's good motivation for us to regulate that AV delay in pacemakers if we can sense it to get the optimal metrics out of these patients. The relationship is strong, but for some of those functional values, it was relatively weak outcomes. For the LV stroke volume, you saw maybe an adjustment of 5 milliliters. And that's not too surprising because we just changed the electrical function. We didn't alter any of the mechanical or structural parts of the model which would, in a normal patient, degrade along with the electrical activation. We did see that the resultant effect on the atria was strong right from the start. So even if the LV hemodynamic function is small, or even though the signal is there but the amplitude is weak, what we see in the atria is a strong signal and a strong amplitude for both, which strongly motivates that patients could benefit for this. And we saw that with mean left atrial pressure, with the E and A flow ratios, and the AV pressure waveform generations. So finally, yeah, we came to the conclusion that this is a worthwhile thing to consider for pacemakers and algorithmic developments. And I think that it's something that I see I'm out of time, but I think it's something that we can always do, right? We can always improve our algorithms and our devices, and modeling is a wonderful tool to help us, find the signal in the noise.
Great. Thanks, Kevin. Just scoot over so the people on this side can see you.
Yeah. It's I don't know if you noticed, but the lights are right in your eyes, right in the center of the screen, so you migrate to the side.
So, any questions for Kevin before we turn to the next speaker? It was a lot of detail on rhythm management. Yes, Wolfgang.
So you need a pressure sensor in the left atrium, and then you're going to have an intelligent pacemaker.
We showed that you don't need that. You just need the electrical signals, and you can infer what the pressures would be.
So, sorry, just to qualify. So based on the model, you can use the relationship and then just implement that.
Exactly.
Based on the input.
Exactly, because almost all devices will have a sensor on them that will give you an EGM, so a local potential. And you can use that to derive the P-wave duration.
Okay, please.
Yeah, for those of us who spend our careers trying to not injure the electrical system of the heart, I couldn't help but realize that you're modeling, you're thinking about it from a device standpoint, but from the flip side, it almost gives you a picture of the health of an individual patient's conduction system, right? And so rather than, thinking about it like, did I cause heart block or did I not? Where on the spectrum are they now, and should I anticipate hemodynamic changes? Because a lot of those patients who don't have heart block or have heart block and get pacing come back with really deranged now function because the pacing wasn't perfect, or we left them with a really fragile conduction system. So it seems like maybe there's an opportunity to apply this in a patient-specific way to really judge the health of the conduction system with much more fidelity than we currently do. It's very exciting data, very exciting.
Yeah, I agree. I think you've outlined a nice area to investigate.
We have a question in the back.
Okay, time for one more.
Super interesting talk. Owen Richfield from Yale. So what you're kind of showing here is what seems to be a substrate for an optimization schema. So wherein you have a device that is controlled such that it will notice, it will read what's happening in the heart and then adjust itself as time goes on. So my question is, have you, first of all, is there interest in simulating that process using the heart model that you have used to get this information in the first place? And then have you changed the anatomy of the heart? Have you changed the mechanical properties to investigate, interpatient variability in this process?
That's a great question, thank you. So your first point, I would say that we have thought of combining that whole optimization program in the simulation. It's challenging because we need, as you know, it was mentioned earlier by one of our previous speakers, these take sometimes 12 to 24 hours to run multiple heartbeats. So to do a live optimization with essentially a control feedback can be challenging, but not impossible. But we haven't looked at that. It's definitely something to pursue further. And we have looked at different geometries and different material properties. It's something that we actually presented at a previous Living Heart Symposium where we helped guide clinical trial protocols. So that's something that we do quite regularly at Medtronic.
Great. I am going to have to cut it off, but I think to that last question, pay attention, I think, to tomorrow afternoon, because I think this is an area where artificial intelligence, using the models to train a faster model as a surrogate, could actually drive that process. Okay, great. Well, thanks again, Kevin.